Okay, so let's continue with the second part of this lecture on data structures. So I'm going to share my slides. So data structures. So what are data structures? Yeah, well, we saw some data structures before, such as a list, but there are many other data structures out there. So a data structure is basically a collection of data on which operations are defined to add, delete, change, and or query the data. Yeah? So in essence, every data structure contains one or more objects or elements, and you can add elements, you can delete elements, you can update elements, update the value or something, and you can search for elements or query. I specify a query that selects a subset of your data. So most, if not all, programs have to deal with input data. So you have the choice of the data structure, which is very important, and not only for your input data, but also for any data you need during computation. And you should ensure that these operations are as efficiently as possible. So there are many data structures in many forms, and they all have their advantages and disadvantages, and you can select them based on your application. So for example, do you need to update data a lot? Is it mainly static data? And so for example, if you have a list and you know that you're not going to add elements, you can just use a fixed size array. If you know you're going to add more data during more elements to your array during processing, then you need to create a dynamically sized array. Is it necessary to access elements at random in your array or other data structure? Or is it also fine if you can read one value at a time in a more serial or consecutive manner? So these types of questions define which data structure is more appropriate and more efficient for the operations in your application. That's what I said before. You have to think what operations are necessary and how efficient each of these operations needs to be for your program's purpose. And if you choose a bad data structure, that means your algorithm will take days to finish instead of a few seconds. So that's again with the complexity, the time complexity. If you have a bad data structure and adding an element takes n square time, and you're going to add a lot of elements, then your program is not going to get very efficient. Then abstract data types. So abstract data types, they're often used synonymously with data structures, but basically they're kind of a high-level abstract description of your collection and its operation. So the difference between an abstract data type and a data structure is that an abstract data type does not tell you how it's implemented. So you can have the same abstracted data type and have it implemented by different algorithms. And so some examples are a list. You have the list abstract data type, and it can be implemented using the array list data structure or the linked list data structure. So these are two implementations. With both implementations, with both data structures, you can do the same set of operations, but some operations will be faster in the array lists, and some operations will be faster in the linked lists. Same is with a set or dictionary or map, as it's often used. It's called a dict in Python, but it's called a map in most other languages or in textbooks. That's also either implemented by a hash table or a binary search tree data structure. But you can use a set, and depending, it doesn't matter if you use a set which is implemented by a hash table or a binary search tree. You just have a set of unique elements, and that's fine. So what are the standard abstract data types in Python? You have lists, the standard list in Python, and that's usually implemented with an array, which uses geometric expansion. So I'll go into that later on. You have a dictionary, which is usually implemented using a hash table. You have a set, which is also usually implemented using a hash table. In the collections library, so that's a standard library in Python, you have order, ticked, and dequeue. So order ticked, it's like similar to a dictionary, but it remembers the order in which you insert elements. And that's implemented using a binary search tree data structure. And then finally, the dequeue are an implementation of both stack and a queue in Python. So let's look at the first data structure, lists, the most commonly used data structure by far. So a list is just a container, and it contains a sequence of elements, and it can also contain duplicates. So you know the list data structure in Python, and so what are the specific operations only defined on a list? Well, positional access, so retrieving an element at a certain index. So list 4, for example, is also sometimes called random access, because you can access any element in the lists using this notation. Then you can insert an element at a given index. For example, if you want to insert 3 at ABBA, at position 3, you can write this. So it's different than changing. Insert does not change the element at position list. It really inserts a new element between other elements. So that's another operation. Index. So index is like the search function in lists. So you type list index ABBA, and it returns the index in the list on which the value ABBA is stored. And then you have the range operators. So that's to retrieve a slice of the list. So if you type lists and then rectangular brackets 4 to 10, you return the sublists starting at index 4 until 10. Other operations on a list are append, which adds an element to the end of the list. So ABC, if you type list append ABC, ABC will be the last element in the list. Delete, which removes an element from the lists, and contains, which is the in operator in Python, which checks if a certain element is present in the list. So these are the essential list operations. You all know them, but what you don't know is, I probably don't know, is what is the cost of running these operations. And if we think about costs, we think about time complexity. So the cost for each operation given a huge list. So there are two data structures you typically have to implement a list. And the first one is a linked list. And I show an example here. So here we have a list ABCD. So the can be integers or string values or characters, whatever. And in a linked list, you actually have little cells, and each cell contains a value and then a pointer to the next cell. So that's how a linked list is implemented. So you have a small array of size 2, you could say. The first index 0, contains a value, and index 1 contains a reference to a new tuple or box with 2 elements, namely the next value in the lists, and so on, like this. And then the other option is to use an array list, which is also default in Python. And an array list is basically an array, but it's dynamically extensible. So that means, for example, in memory, you store all the elements just in consecutive memory places. So you have A, and for instance, if A is an integer, that means 4 bytes. So you reserve 4 bytes in memory to store A, and then directly to the right of that in memory, you store the next value B, C, D, and so on. So they're just consecutive places in memory. The difference with an array list is that you have some free space. So in Python, if you create a list with these 4 elements, actually behind the screen, you might have a 5th and a 6th and a 7th spot, but they're empty. So there's a difference between an array list and an array, is that an array list is actually an array, but with some extra capacity. So here the length of the array is 4, but the capacity is 5. You reserve an extra spot if you want in the future, for example, to append an item. So both the linked list and the array list have their own advantages and disadvantages, as we will discuss in the next slides. So the first operation we're going to look at is insert. So for example, if you have a list, A, B, C, D, and you insert element X at position 2 or at index 2, it means, because you start with index 0, that you're going to insert X after B and before C. So if you have the array A, B, C, D, after this operation, you will have A, B, X, C, D. So how is this implemented? If you have a linked list, that means you go through your list, you start at A, then you find the elements after A, which is B, and then we want B is at index 1, and we want to insert X at index 2. So then we modify our array list, and we reference a new cell, which contains X as a value. We reference from the cell, the next cell of B becomes that new cell containing X, and then X will point to the old next cell of B, namely C. So we can update that in this way, and actually it's very efficient to do that. We say it takes constant time. Given the cell to B just means you update the reference, and you point to this new cell containing X, and then it points to C instead of B pointing directly to C. But if you have an array list, it gets a little bit more inefficient. So if you insert an element X at position 2, that means first you have your original array A, B, C, D. Then it could be that you have to copy it. If there's no more free slot here, there's no additional capacity, and your array has only 4 elements, then you have to resize your array to an array of 5 elements, and also all the elements after index 2 have to be moved one place to the right. So if you're going to insert X, that means C is at position 2, so C is going to be moved to position 3, and D is going to move to from position 3 to 4, and so on. And so that's less efficient. And if you have a really large array containing millions of elements, and you want to insert a new element at the second position, that means all those millions of elements have to be moved one position. So that's not very efficient when it comes to inserting. Another operation is appending. So when you use array, an array always has a fixed size. And even in a dynamic array, if you don't have enough capacity, that means you have to double the size, for instance, of the array, and then copy all the elements you had in memory to the new array, which is bigger in size. So that's how it works. So when you append items to the end of a list, and the array is full, there's no more capacity, then you have to create a new array, copy all the elements of the old array to the new array, and this cannot be done in constant time. While with a linked list, you can just add a new cell at the end of the list and create a new pointer to that last cell. So actually for adding an element, the linked list is much more faster. There's one detail here, and that is if you have an array and it has free capacity, then appending is quite fast. You can just add the value to the end of the list in a free slot. But once in a while, your array is going to get full, and then you have to resize the array and copy everything. But we can say in the worst case, appending to an array list is ON, but amortized, so average over different runs, it actually runs also in constant time. So that's about appending. And so this is a small overview of array list versus linked lists. So you can see random access in an array list is very fast. It's constant time because the values are stored consecutively in memory. It's very easy to get a random element from an array list. While in a linked list, you have to remember they're all cells linked to each other. So if you want to have the fifth element, you really have to start from the beginning of the list, the first cell, then go to the second cell, third cell, and so on, until you have your end cell. So that has a time complexity of ON. If you look at append, remove, and insert, however, you can see that linked list is very efficient. If you want to remove and insert elements at random positions using the linked list representation, is much more efficient. Here I assume an iterator, otherwise it's ON. I'm not going to go into details about that, but the time complexity is really nice. While for an array, if you want to remove or insert an element at a random position, you will have to resize and move a lot of elements. So in the worst case, it's ON. Then finally, contain and index. Contain is just to check if a certain element is in the list. Index is to return the index of an element in the array. So these are both these operations require you really to go over every element in the array and check its value against the arguments. So these are operations that have a complexity that's linear. So we will see later on in this presentation that we can improve that using a hash table or a binary tree. Okay, so the next data structures are stack and queue. So a stack is a data type, and it restricts access to the most recently added element. So you can think a stack as if you have lots of documents and you put them on your desk, you put them one by one on top of each other, and you can only access the document that is on top of your paper stack. So this is the same data structure, but then for programming. So it's called last in, first out. So the last element you put on the stack is actually the only element you can access. So you have three operations when using the stack abstract data structure. Push, which adds a new element on top of the stack. Pop, which removes the element on top of the stacks and returns it. And peek, which allows you to just check the element on top of the stack. But you can only access the top of the stack. So for the stack ADT, we want every operation to be constant in time, and that can be implemented quite easily using an array list or linked lists. So that's the stack. Here's an example, some example code. So you have an empty stack. Then first I push len, then I push dieter. If I then call the operation peek, which is the top of the stack, it prints dieter since it was added last. So len is below dieter if you want it to see it like this, like that. Then you can pop the stack, which will return dieter and also remove it from the stack. And then if you again look at the top of the stack, this time you will have len. So that's a stack. The stack is complementary to the queue. So a queue is like a queue in a supermarket. You go and stand in a line, and then you only get one by one you go in line. So it's first in, last out. So with the queue, again, we initialize here some sample code. You have an empty list. And then we enqueue len. So len is the first in the line. Then enqueue dieter, which means dieter goes in the back of the queue. And then if you print the front of the queue, it's len, because len was there first. If you dequeue the queue, you get the first customer or the first objects removed. So len is removed. And if you then look who's at the front of the queue, it's Dieter. And so the stack and the queue are two simple data structures based, usually implemented using array lists, and they're used quite often in algorithms. And so all these operations like enqueue, front, dequeue, or for the stack, push, peek, pop, they're all run in constant time. Then the next set of data structures, set and map. So set you probably have used in Python. It's also as the set data structure in mathematics. So a set is basically a collection of elements, but you do not allow duplicate elements. Also, by definition, a set has no order. So in a list, all elements are in a certain order as specified by the index. In a set, there's no such order, unless you have a sorted set, which does provide you to order elements, and also, but in contrast to a list, does not allow duplicate elements. So in Python, you have the set keywords. It's built into the standard language, and actually a set is implemented using the hash table data structure. You also have a sorted set, which is typically implemented with a binary tree. It's not standard available in Python, but collection or dict comes close. Then you have a map. A map is a collection that maps keys to values, and it does not allow duplicate keys. So each key is unique and maps to one value. And so you know map from Python, because actually a map is a dictionary in Python. And usually it's implemented with the hash table data structure. There's also a variation of map, which stores the keys in sorted order, and that's a sorted map, and that's implemented with a binary tree. And in Python, this is the ordered dict data structure, or abstract data type. So let's talk about trees. So binary trees, what is it? So a tree is a collection of nodes, and you have one root, and then you have edges to all your subtrees. At the bottom of the trees, the nodes are called leaves, and there's one unique path from each root to each leaf. So that's a basic tree in memory. So in memory, you can implement it with tuples, and every tuple has a value, which is the node value. And then for every branch, you store the other nodes recursively, or with a pointer you reference to subnodes. So what is a binary search tree? So as I mentioned before, it's used in ordered dict. It's a type of tree. One difference is that it only has 2 branches for each node. And so here the root has 3 branches, and then here you have 1 branch. With a binary tree, you always have 2 or 1 subtree. So if you use the binary search tree data structure, then the average execution time for most operation has an average time complexity of log n. So that's very nice. Log n scales with big data inputs. However, the worst case is still on. So in the worst case, it's not that efficient. However, in practice, there are some advanced data structures like the balanced red-black binary tree, and then the worst case is also guaranteed to be logarithmic in the number of elements in the tree. So it assumes that all nodes are ordered based on a key. So often the key is part of the data. So the order property states that for each node, all keys of nodes in the left subtree are smaller than the key of X, and all nodes in the right subtree are bigger than the key of x. So here's an example. So you have your tree, and then you have the binary tree here. The root element is 5. That means that all elements at the right and in the right sub-branch of 5 are bigger than 5, and all elements to the left in the left subtree are lower than 5. And then that continues recursively. So 7, for instance, is higher than 5. So that means it's guaranteed to be in the right sub-branch. Then you have 8. Then you know 7 is smaller than 8, so you know it's guaranteed to be on the left, in the left subtree. And there you find element 7. So that means that if you have some kind of list of data and you create a binary tree of that with an algorithm, that you can then search the binary tree, and it's very efficient. So it's only O log n time. So remember before, if we use the list, if you want to search a certain element in the list, you really have to look at every element in the list. So that's O(n). But here it's only O log n. And so why is it logarithmic? Because every time you search a tree, and every time you split the tree into two parts, the left and the right part, so that's a bit like quicksort, the divide and conquer rationale. So instead of searching the whole tree, after only comparing with 5, you can already discard half of the data, because half of the data, you can assume that half of the data is in the left tree, and you can ignore that because you know 7 is bigger than 5, so you only have to look at the right tree. And then you go to 8, and then again we have partitioned all the data into two subtrees, data that's lower than 8 and higher than 8. So because of that divide and conquer strategy, you can assume a worst case of log n. So search is sufficient. Also addition is the same principle. If you want to add 4, 4 is smaller than 5, so you go to the left subtree. Then you have the subtree with the root 3. 4 is bigger than 3, so you go to the right subtree. Then maybe you don't have any more nodes, and then you can add 4 as a new node here. So 4 is the key here. So in this example, we could store just numbers, but you can also have like an association where 4 is the index, and then you store, for example, all the attributes of a user with index 4 or something like that. So adding also takes log n time, because the depth of the tree is at most log n. Removing is a similar principle. So here we want to remove element 5. So that means 5 is going to be removed, but we have to take some care because we have a tree here, and we have to make sure that we have a tree where every node has a value, and if that's lower than the value, you go left, and otherwise you go right. So if you remove 5, that means you check the minimal value in the right subtree, which is 6, and then remove 5 and replace it with 6. So 6 gets swapped here with 5, and then your element 5 is removed from the tree. So that's also an operation that takes log n steps. So in conclusion, tree, if you want to remove any element, insert any element, search for an element, or also find the minimum and the maximum, you can assume the average complexity is log n. So even if you have millions and billions of data points, if you have a million of data points, log 10 of a million is only 1,000, so you need only 1,000 comparisons to remove or find or insert any element. This is assuming a balanced tree, because in the worst case, we can still have a complexity of O(n). So that can happen if the tree is not balanced, but more, if it's more sorted, if it's more like a list, where you never have a partition and the left branch is always empty, your tree might resemble a list, and then in the worst case it's O(n). But you can, if you assume a balanced tree, and there's some algorithms that guarantee your tree is balanced, then you can also then it's also guaranteed that the worst case is as a complexity that's logarithmic in the input size. Then finally, hash tables. So a hash table, it's something special. I really like this data structure. It's super efficient, and actually it's not that difficult. So it's the data structure that implements the abstract data types set and map, and it uses hash functions. So I'll explain it in the next slides, but it's based on hash functions, do lookups, additions, and deletions in constant time. So it's a binary tree. It was logarithmic time. Now it's even better. It's constant time. So adding or searching for any element is independent of the number of elements you have in total. One disadvantage of hash tables is they're not suited for finding the minimum or maximum elements, or also any types of operations that depends on sorting. So if you require a sorted data, you should choose a binary tree, and otherwise a hash table because it's more efficient. So what is the hash function? Well, a hash function is basically a function, and it maps any objects. So in this example, I have a string objects, but it maps any object to an integer within a given range to be used as an index into an array. So for example, with an array, if you have an array of 10 lengths, you have indexes 0 to 9, and it takes constant time to just reference any item. If you just want the 5th or the 6th element, you can just use that index and get the value in constant time. But the problem with arrays is they don't work if you have strings. So what is the hashing function? It takes a string object and it transforms it to an index into an array. So to an integer within a certain range. And I've shown you an example of a hash function here. So example, you have the string Pheromans, and you want to store that in an array. What do? Well, first you take all the characters, F-A-R-A, mans, and each character you translate to a number. For example, if you only have lowercase letters, you can represent each letter as a number between 1 and 26. So Pheromans actually becomes this array, 6, 5, 18. So 6 is because F is the 6th letter in the alphabet, E is the 5th letter, and so on. So you store, instead of Pheromans, you store this array of numbers. That's the first step. Then the second step, you have, like in Pheromans, you have the E, but you have both at position 2 and 4, and they're both encoded as 5. So to make sure that each number is unique, you want to encode its position into the string. So actually what you do is you loop over all the numbers, over all the letters here translated from ASCII to numbers, and then you multiply each number with the power 26, because you have 26 letters, times E, and E is the index. And if you do that, each number, the numbers become very large, but that's not important. But then each number is unique. So you encode not only the character value, but also the position. So here, for example, for the E, at the 2nd and the 4th position, they get a quite different number. Then you add all those numbers of that array. You just add them, just take the sum, and then you compute the remainder of the division by 1000. So if my array contains 1000 buckets, you do the division by 1000, and then you get a number between 0 and 999. So that's just the remainder of the integer division. So if you repeat those 4 steps, you can map any string object to a unique code between 0 and 1000, and that's called a hash function. So what's the advantage? And here's an example in Python. You can now have an array of 1000 elements, and we can store strings, and we can have a string And if we call the hash function, we have an index in that array, because the hash function returns a number between 0 and 999. Yeah, so here is an example in Python. So if you have an empty dictionary, and then in the dictionary you have first store some information about the user pheromones. So that means in the dictionary with the key, you use pheromones, and then you store some attributes. And you do the same for Dieter Brugmans, indexed by Brugmans. And then maybe you have 998 other names, other users you want to add to your dictionary. And then you can look up pheromones in the dictionary, and that lookup, so returning all the attributes associated with the key pheromones, does only take constant time. So even if you have millions of elements in your dictionary, that lookup will only take constant time. So internally, what happens in Python is you have your dictionary, which is actually an array. It's an array list, to be exact. So it's a dynamically sized array with 1,000 elements. And if you look up a value in the dictionary, you compute a hash of pheromones. It gets a number between 1 and 1,000. Here it's 465. For the Brugmans, with that key, you have another hash function, and you just go to the array. And in that position in the array, you can then store all of your attributes associated with that index. So that's how it works. Very nice. So one problem with a hash table, what if two strings hash to the same index? So the hash function, basically, it returns a kind of random number between 0 and 1,000. And it could be that two strings have exactly the same hash function. So that's called a collision. So what happens instead of an array, there's a different solution, but one is instead of having just the array with all the buckets, all the indexed by hash functions of the index key, you store not one value but a list, a small linked list, for instance, you can store. So then if you have two strings with the same hash index, then you just store those two values within a linked list for that array position. So that's how you do it. So a hash function should be fast to compute and divide elements uniformly across the allocated space. That's why I designed this function. It's to make sure that every string gets a more or less unique ID, which is spread uniformly over the range, so between 0 and 1,000. So that's important. And also the capacity of the hash table is important. So usually the number of elements in your hash table or buckets is chosen relatively to the number of elements you're going to store. And so if you're going to store 1,000 elements, you will also want an array of about with 1,000 elements. And here's an example. So if you add the following keys to a hash table with size 10, 89, 18, 49, 58, 9, and 1, you compute the hash of it, and maybe the hash of 89 and 18, 89 and 49 are both 10. That means here in that array, you're going to store those in a linked list. So you could argue then, then it's not constant time because you have 3 elements here. And it's true, but still, if you have millions of data points, then, and if your hash function is really spreads the elements uniformly, that means in the worst case, you will only have a small, in the average case, you will only have a small number of buckets, a small number of elements which exactly have the same hash code. So that's how a hash table works. So if you look at the runtime of the operation, remove takes constant time. It's just you compute the hash function and go to the array at that hash position and remove an element. Insert, it's the same. Contains, also the same. Defining the minimum, the maximum does take a long time because actually it's not supported by the hash table. And so that means you just have to loop over all elements in your hash table. So that's something you can better do with a binary search tree. Okay, so that concludes this small dive into data structures. Here's an overview of common data structures in computer science. So we start an array or array lists, stack, linked lists. There's some variation. You can have a single linked list or double linked lists, a hash table, binary search tree, and then there are some more advanced trees like a red-black tree, which guarantees that the tree is balanced. So the worst case, the worst time complexity is still logarithmic in the number of elements. So voilà, this is a small overview. So that concludes this presentation. I have some additional material. I'm not going to explain it, but you can have a look at it during or before the lab session this afternoon. So some slides on the implementation of a binary search tree with recursive operations, explain a little bit, and then also some slides on how you can implement your own search engine using a hash table. And so this is just additional information. You can look that up in your own time at home or during the lab session this afternoon. Okay. Are there any more questions about data structures? Is it all clear? Or are you all confused right now? Any questions? All clear? Okay, so this afternoon there's a lab session. You will practice. I think the first exercise will be to do some implement some sorting algorithms, then some exercises on data structures, and then some application which involves full text search. So see you next week. Bye.